Hello and welcome to Easy Projects. So today we will continue the FPGA and VHDL series, and we will finish this counter that we began working on in the latest video. We will get rid of this stuff that we don't need, and we will have to add some features that we do need. But first we'll take a look at some of the development boards that are available. I forgot to do that in the previous video. So we'll start by looking at the terasic.com.tv website. This is the manufacturer of my board, and they make development boards with Altera FPGAs. Their lowest range, the smallest and least expensive boards are the DE0 series. They have the DE0 Nano and some regular DE0 boards. I think there's two of each. This one is particularly interesting because it's a system-on-chip solution, so you get both an FPGA and a processor in the one chip. And this is actually a very powerful little beast. But let's start by looking at a regular FPGA board, and then we will go back to the system-on-chip in a little while. So one of the things you want to look for is how many logic elements there are on the chip. In this case we have 49,000. And I can't really tell you how much you can put into this, but as a general rule, of course, the higher the number, the more stuff you can put into it. But if we reference it to this one, I think I might have a report of this. You can see we use 30 elements to make our counter, plus this regular logic stuff. So you can do the math and see how many of these you could fit into one FPGA. So it's a quite powerful chip that you get on these boards. Some other stuff to look for is how many I/O pins you get. In this case it's 40, 2 times 20. You also get on this board a VGA, which has a 4-bit resistor DAC. It's not great resolution, but it will allow you to put something onto a screen. And you can see we have 10 onboard LEDs, 10 slide switches, 4 debounced buttons, a CPU reset push button, and 6 7-segment displays. Okay, the CPU, I couldn't quite understand that. That's just an FPGA reset. So they shouldn't really put CPU there. But so this is an okay board for beginners. It's a fairly capable FPGA, and you won't fill that up the first 2 days, that's for sure. A bit larger boards are the DE1s, and they get a little more peripheral stuff also, more switches and more displays, and more I/O. And then finally we can go to the DE2 boards, which this one is the one I've got. That one has 114,000 logic elements, or 115 they use in the name, but then it has lots of switches and LEDs and some 7-segment displays. It also has a character display, which I have used, but then again that's only like $2 from eBay, and you can make your own little cable to plug in, so that's not the big deal. I wouldn't really recommend these expensive boards for beginners, unless you know you have to make some very large designs in the future. This one is the cheapest they've got. If you're a student, you can get it for $61. It has 22,000 logic elements, if I remember correctly, and then it has a lot of I/O, so you can make your own adapter boards or whatever and connect your own stuff to it. It's a very small board, but still plenty powerful for a beginner. But as I briefly mentioned earlier, this system-on-chip thing is becoming very popular, and for good reason, because you want to crank as much power as possible into as little device as possible, so you of course want to take your processor and put it into the same chip. If we take a look at this one, you can see you don't get any displays or a whole bunch of LEDs. You only get these 4 slide switches and a few buttons and some LEDs. But then you have all these I/O pins that you can use. and connect up your own stuff. But the SoC chip on this board is very powerful. You get an FPGA with 40,000 logic elements, but then you also get an on-chip processor. It's a 925 MHz dual-core ARM Cortex-A9 processor, 1 GB of DDR3 SD memory, an accelerometer you can play with, and a whole bunch of other stuff. So FPGAs are good for a lot of stuff, but often you'll realize you need a processor to process some data. So in the past, what people have done, and it's still done, is that they use some of the FPGA logic to make a soft-core processor. So you can run code on that processor, but it takes off FPGA hardware, which you don't really want, and it's not as efficient as having a dedicated processor. There's no way you will get 925 MHz on a soft-core processor that you made inside the FPGA. So that's why they started to include them, because they know a lot of people have to use both an FPGA and a processor. Unfortunately, I don't think I'll be looking into this anytime soon in my series, because I don't have one of these SoC boards and I have no experience with them, so I'd have to work with them a little bit before I could do a video on it. Another thing is, I don't know if they program exactly the same way as I have programmed mine, if you can just ignore the processor altogether if you don't want to use it, or if you have to set it up in some way or the other. So if you are going to get one of these boards, then you might look into that. So you might think these boards are a little bit expensive, and why not just buy the FPGA and make your own board and get it a lot cheaper, right? But there's two problems. One is that most of the powerful FPGAs are in BGA packages where the connections are on the bottom. So you can only solder them in a controlled reflow oven if you want to make sure that you get good connection. And then the other problem, if you take a look at this DE0CV board, if you're a student you get it for $100. And the chip itself costs $66. Then you would need all the displays, the buttons, the connectors. You need to make a PCB. You need some RAM, some flash memory, some power supply stuff, and you're not going to make that for $40. And even if you pay the full price, you're probably not going to make it for $90 either. And I think this was the one where there was most difference between the board price and the chip price. If you take a look at the Nano SoC board, you can get that for $90 if you're a student, or $100 if you're not. And the chip itself, one-off price at DigiKey is $140. So you pay less for the board than you do for the chip. So don't even think about it. Of course, you might be more interested in Xilinx than Altera for some reason. And I think the most popular boards among hobbyists and beginners are the Digiland ones. I just scrolled through this and read a little bit about some of the boards, and the thing I found is that you seem to get less I/O on these boards than you do on the Altera ones. The good ones that I found was either this top one or some of these ones down here. You shouldn't be tempted by these prices, the 25 and the 75, because that's only CPLDs. And as I explained in my first video, they are not nearly as powerful as FPGAs. But let's take a look at the top one. So here you get 33,000 logic cells. And I guess this would be somewhat equivalent to the logic elements of the Altera ones. But then you only get 4 PMOD connectors. And I think these are 2, 4, 6, 8, and yeah, they're 12 pin each. So you get these 4 by 12 pins, which you can use for your I/O. Let's quickly look at one of the Sync chips. This is Xilinx's answer to the SoC chip from Altera. You can see here we get a 650 MHz dual-core Cortex A9, and we get a 28K logic cell FPGA. So you can see it's a little more expensive than the Terasic board, and in my experience, now I look through them, it seems like you get a little more bang for your buck if you take the Altera one over the Xilinx one. But you might disagree, and you might have a reason to take one of these, and that would be okay with me, of course. You take whatever you want. When that's said though, I think the Xilinx software is a lot better than the Quartus from Altera that I'm using. But once you get used to it, yeah, it's okay. But when you have to make test benches and simulation, then I really like the Xilinx a lot better than the Altera. I can't really say which one you should get, but my advice is if you're a beginner and you're not really sure what you want, then probably take either the regular Nano or the Nano SoC. I think the SoC one is without competition where you get the most for your hard-earned dollars, so that would definitely be a good choice. But then again, I don't really know if it programs the same way, and I don't know how to use the Cortex A9 yet. My guess would be though, and it's only a guess, that when you hook up the JTAG cable, it will come up as two different devices, an FPGA and a processor, and you can just program the one that you want. But again, I'm not sure, it's just a guess. Maybe we can get somebody who has this board to comment on that. So that was a quick, if we can call it that, look at the development boards available, and now we'll get back to the counter that we're making. So this is what should increment our clock, and we need to get rid of some stuff, all these inputs here, and we need to add the stuff that we will need for the counter. So most counters will have an enable input to enable the count, and they will also have a way to reset them. This we can do two different ways. We can make it a synchronous or an asynchronous reset. The synchronous will be dependent on the clock, so it will only reset if the reset is high while there is a rising edge clock, for example. If you hit it in between clock periods, if you can do that, then nothing will happen. The asynchronous doesn't care, that will reset it no matter what. I think we'll go with the synchronous reset. Then we will need, I don't think we need any more inputs, so we can get rid of that one. Then we need, since we are not counting to a binary number to the power of 2, for example, then we really need a terminal count, which can tell when the counter has finished counting and wraps around to 0. And we'll call that TC. So this will go high for one clock period when the counter has done counting, and it starts again from 0. And I would like to get the clock in the beginning, up here. It doesn't matter where you put it, I just prefer it this way. Usually I'll arrange it so that I have all the synchronous stuff together, and if I have some plain old logic, then I would put that by itself like I did before, where I had the A, B, C and Q up here and the clock and output down here, so that this stuff up here wasn't really related. You can do it however you want. But we will, of course, we need the output to be 6 bits, so 5 down to 0. This will allow us to count up to 63, but we only want to count to 59 before we start from 0. So we'll also need a way to tell the counter when to reset. We could do that a few different ways, but it would be easiest to make a new input. And then we can call this Tcount. Not that word. That's better. So we could take this input signal and make the counter in a way that when the output reaches this value, it will reset and start from 0. That way we can change the number on the fly if we wanted to. Or you could wire this to some switches or whatever signal you wanted, and that could program the counter if you wanted. That would be a very good solution in many cases, but in this case we wanted to always count to 60 because Usually there's 60 seconds in a minute. So we don't have a need to change it on the fly. Then we can actually do this in another way, which is simpler, and it will allow our counter to be more versatile. So we'll get rid of this for now, and we'll take a look at something called generics. You can think of standard logic and standard logic vectors as plain old wires that connect stuff inside the FPGA. But we can also use generics, and you pretty much make them the same way as the standard logic. You just write the name. In this case it's Tcount. Then you write a colon and the type. And now you don't have to define if it's an input or an output or whatever, because that doesn't make sense. We'll get to that in a minute. You can make it a natural. And what this means is that it's just a number. And then we can make another one. That would also be a good idea. And we can call that n bits, or perhaps just n. And some people like to use single letters for this. And I guess that's a good idea, but for now we'll call it Tcount so we can remember what it is. So this generic actually has to do when we instantiate the counter. We will make a top level file where we create the different counters that we need. We will need one for the seconds, one for minutes, and one for hours. And we would like to use the same counter for all of them. So when we use this counter in that file, we can send some values to the counter if you want. And that's what the generics are. So we will send it a number, Tcount, which should be the number we want to count to. And this n, let's just call it n bits. And this will be the number of bits in the counter. Right now you can see it's specified to 6 bits on the output, and this down here we didn't touch yet, but that would be 6 bits also if we wanted to count to 60. But we also need one that only counts to 24. We could still use the same one and get 6 bits, but that would be a waste of hardware. So we include this n bits so we can specify how many bits we want. That way we can also use it to count to 5 million if we want. We can just change these two numbers and use the same code down here. So instead of 5, we'll write n bits and then -1. So that's that. And we also want to change these. And then we can just get rid of this because it's the same. Maybe it will make more sense if we give these a default value. Let's say we want it to count to 59, or should we make it 60? That depends on how you implement the rest of the hardware, if it should be 59 or 60. I think we'll do 60 though. That'll make most sense. And then the number of bits. As we said, that should be a 6-bit counter. So you can actually think of this as defines in C code. So if you define Tcount 60, then every time you meet this name, you'll just substitute it with 60. And the same for the n bits. So this would really say 6 minus 1, and the same down here. But the thing is, you can change this when you create a new counter. And we'll get back to that, so don't get confused by this just yet. So now we'll take a look at making the actual hardware for the counter. And what we have now is simply a counter that always will increment the count. We're not looking at enable or reset or the Tcount generic up here. So in order to do that, we will need to add some more if statements. And by the way, first we're going to do this in a spaghetti code way. That will get a little bit messy and hard to understand if you were to read somebody else's code. You would probably be able to figure it out if it was your own code, but in the end we want to convert it into a more comprehensible format, so if somebody else sees it, they're not going to drop dead. But first we want to do it with a single process and if statements, so we can see how they work. So we'll make one if the reset SRST is equal to 1. Then we will make the count out. And then we'll do others to 0. Then we'll make the end if before we forget. Oops. So now we have a synchronous reset function that works in a way if the button is held when the rising edge of the clock happens, then it will reset back to 0. Then we need an else if, and that's written ELS if. Then we want to check the Tcount also. So if count out is equal to Tcount, then we also want to reset. And the reason why I don't do this in the same, I could just, if this is what we wanted to do, then I could just have said if reset is equal to 1, or then this expression count out equal to Tcount. But since we only want to pull the TC high if the counter is reset by this expression, then we can't do it in one if statement, then we have to make two different. And if none of that is true, we have to check the enable. And then we need to do this. And if we had something, a default thing that it should do if none of the other were true, we would write else, like that, and then just write whatever down here. So the structure is if, and then you can have some else ifs, and then you can have else, and then it should end with end if. But in this case we don't have an else, at least not for now. But we also need to put this TC back to 0 again. So we can, that could be the first thing that we do in the process. And I don't think I mentioned in the previous video, as soon as you're inside a process, then you can assign the same signal different values throughout the process. It will just take the latest one and assign that to the signal. So you could do this, that TC is equal to 0, and then down here you set TC equal to 1. Then it will only do this if this condition is true, of course. It's just outside a process you can only have one like this. And let's see if this will compile. Oh, that was a stupid mistake. But actually I made one little mistake here. If you think about it, we're counting to 60. But since this is all synchronous and we check if the count out is equal to Tcount, then we will only reset when this has been 60 for 1 second. So we will actually get 61 seconds, and we don't want that. So in this case we would have to specify this as either 59, or we would have to say Tcount -1 down here. So let's quickly recap this. If we get a rising edge on the clock, we will always set TC back to 0. We will check if we have a high on the reset line. If we have that, we will reset the count. If we didn't have a reset, we will see if our count out is equal to Tcount -1, meaning that 60 seconds have elapsed. And if it has, we will set the count back to 0, and we will set the TC high. And if none of this happened, then we'll go to this one. We will check if enable is equal to 1, and if it is, we will increment the count by 1. And by having this enable pin, we can use the same clock for all the counters, and then we can just link the enable pin to the TC pin of the previous counter. So this code is actually not as messy as I thought before I began programming it. The only part is really this TC that we clear up here, and then we set it again down here if this condition is true. We will get back to the other method anyway though, but first I think we will take this block that we made, this chip if you want, and we want to make a top-level file or top-level entity, and that will have an architecture where we will implement a few of these to make our counter. So we will copy all this stuff, and I'll make a new file. Let's make it right there, VHDL. Then we will paste it. And now we will have to rename this entity, so we'll just call it counter. Maybe with a lowercase c. So that should be it. And we want to save this file in the big clock folder and call it counter. So now we saved this file and we should be able to see it in the Files tab. So now we got this in a safe position. We go back to this and we can clear all the stuff here in the architecture. So now we're designing the top level. So this is basically what connects to the development board. So the physical pins on the chip is what you interact with in the top level entity. So we want to get rid of this generic also. We want to use a clock still. The enable doesn't really make any sense. The reset, we can still use that. It wouldn't make sense if you are making a clock, I don't think, to have a reset that would reset everything. But we will keep it for now. The TC output, we don't really need that either. So we'll get rid of that. The output for a 60-second counter, we will need 6 bits. And here we have to specify it because we need to connect these to physical pins on the board. And I guess that's really what we need. Of course, later on we will have to add some plus and minus buttons to set the time on the clock, but we'll get back to that. Now we'll take a look at how to include or instantiate this block of code that we made up here. And to do that we will use entity instantiation or direct instantiation. What we do is we type a label first, usually. We need a prescaler now to divide the clock down, as you saw in here. The output and the number of counts are the same number of bits, so we can't do the trick we did in the previous video where we just made this larger. That wouldn't make any sense to do now that we have this generic that we use. So we'll have to do that in here. The first one should then be a prescaler. And we make a label by writing a name and then a colon. You can also do this for a process, by the way, if you want. We'll look at that in a moment. Then you write entity. And then we will write work dot the name of the entity, that was counter. Then we go to a new line. You don't have to, but it looks prettier. And then we write port map and then parentheses. And now we need to map which pins in this entity, and also you can use local signals in the architecture. But which signals here should connect to which signals in here. We can see the first one is clock, then we have enable and reset. So we will do that. The clock should connect to clock, and you use a forward pointing arrow. The first signal is the one in the target file, if you want, and this last one is the signal in this file. And then we have the enable, but we don't have anything to connect it to, and we need to put it high for the counter to work. So what we can do is to write a 1, and then it will always be high. Then we can go to the next line, and we had the, was it the TC? Yes. And you can do this in any order, by the way. But the terminal count of the counter, we want to connect to the next one, so the actual seconds counter. And we cannot do that directly, so we'll have to make a local signal for that. We will call that, we can just call it TC, and then pre 2 second counter. It's a long name, but it's very descriptive, so. Then we connect that to that. And now the output of the prescaler, we don't need to connect to anything. And it might be okay to leave it out, just ignore it. I don't really know, but you can do output, and then you can connect it to open. And what that will do is make sure it doesn't connect anywhere. And let's just check that you are indeed allowed to do this. And it looks okay. And you would do the same thing with a label for a process. So we can write counter process, and then make a colon. So if you have many processes, this is a good thing to do. Or of course you could make comments with double dashes, which I forget to do, but you should write comments on your code, of course. But we also had this generic Tcount and the number of bits. So we will connect those in the same way. We'll type generic and then map. And then it was called Tcount. And now this Tcount should be the division ratio between the input clock and 1 second. And since we have a 50 megahertz clock, this should be 50 million. Like that. And the number of bits should be, what is that? 50 million. That would be 26 bits. So now what this generic map does is when we put these numbers in, and you might already have guessed it, it goes in and changes these default values. So this will now be 50 million and the number of bits will be 26. Then it automatically scales the entire counter up. It of course takes more hardware, and this way it's very efficient. If the next counter should be only 4 bits, then we could do that. We could use the same code to generate a 4-bit counter as we do to generate a 26-bit counter. It just makes things a lot easier, and you only need to have one file instead of 10 different files if you had 10 counters. So now we want to make a 60-second counter, so we do that. Counter 60 seconds, and we write entity work.counter. Actually, we can just copy the whole thing. Clock should still be connected to clock, reset to reset, and now enable should be connected to this one. So we do that. And now the TC of the 60-second counter shouldn't really connect anywhere for now. But we do need to connect the output. We'll just fix this first though. So 59, no, 60, sorry. We fixed that. And then the number of bits should be 6. Now if we just connect output to output, we could get a problem because If this changes, then it doesn't match this anymore. I don't even know if it will allow us to do it in the first place, but we can try. We have 4 errors. What does it tell us? Generic. Yeah, so we do need to maybe do this the other way around. Oh yeah, okay, I made a mistake here. We need to put the generic map first. So we'll just do that. And then we remove that semicolon there. Yep, so sorry about that. And now we're back to checking if we can just connect the output directly. It's not a good idea to do it anyway, even though we might be able to. Yep. So it knows that this is 6 bits, and that's why we can connect it. If this was 7 bits, then it wouldn't allow us to do this. Now in our case the bits do match up, but you could come in a situation where maybe you had 4 bits output and you only wanted to use the last 4 bit of some counter. Then you might be tempted to do something like this, where you write output say 3 down to, down to 0, should connect to whatever 4-bit output you have here. And Altera will actually let you do this and compile it and put it onto the chip, and it will work. But it's generally not supported by VHDL that you do this. And one example is the Model Sim software. This does not support it. And I tried that myself. So the way you would do it instead is you create a new signal. So let's say we had a standard logic vector, and I will make it 6 bits in our case, and we will call it count out to output, something like that. Then we'll put this name into the counter, and now you just make sure that this and this is the same size, and then you do here, you take output should now be connected to this signal, and then you would write your bits here. In our case we don't have to because they are the same, but something like that. So what this will allow you to do is to, for example, have a 10-bit counter, and you want to count to another value, of course, but then you make this signal 10 bits, and you can still use this because our output is 6 bits. So that would be the proper way to do it. You shouldn't really do it down here. Anyway, let's get back to our 60-second counter. So we're back to the original values here, and let's just see if this will compile and if it can fit it into the FPGA. Then we'll just quickly recap it, and we will upload it to the board. Oh yeah, of course. This doesn't work. It's I copied this line up here, so I forgot to put this in. Maybe some of you were screaming at me, but you know what? I can't hear you. Hopefully it will be better this time. And by the way, if I make mistakes like this, I will probably put an annotation in the video, so you don't buy it first time until I correct the error. So if you have annotations enabled, you might already have seen me comment on that. Okay, so we compiled the design successfully, and we'll just recap this. So the inputs and outputs are fairly straightforward. We still need to connect these to the correct pins, of course, but we get a clock in and we will have a reset button, and the output should be to the LEDs. Then we created one instance of the counter here. We use this as a prescaler, so we can get the clock divided down to our 1 second increment for our counter down here. This counter will be counting once every second, and it will reset at 60. And we could simply copy this and make a 1 minute counter, or sorry, 60-minute counter, and then copy it again and make a 24-hour counter. To connect signals between these two, we use local signals, and we created one to connect the TC of this counter to the enable of the next counter. And we also made one to connect the output of this counter to the output pins. We could probably have done this just by writing output here, as I said, but then if this number of bits change, then this won't match anymore. And now that we have already done it this way, we can just change this number and this number. These will always have to match, so that this is a 6-bit value and this is 6 bits. If we change this to 10, we would change this to 10. So that is that. Now let's connect to the correct pins on the board. So you can see there's a lot of unknown signals now, so we just get rid of these old ones. You can just delete. Sorry, you have to select them over there. And if you have to delete a lot of signals, it's easier to do it in the assignment editor. This one, I guess. We'll just close this so we can see. Yes, assignment editor. Here it won't ask you all the times. So if you want to delete 30 signals, if you do that in the pin planner, it will ask you 30 times, do you want to delete this? And you have to click yes every time. Here it doesn't do it like that. So we'll just get some pins. I can remember the first button is M23. And we'll have to find the next of the red LEDs. And that's F18 and E18. Like that. Now we can close this. And we need to compile the design again to map it to those pins. And now we can upload it to the board using the program device. We'll add the file. And I'll turn on the camera, and then we'll take a look at the board when I upload the file. So here we get our usual light show. And I'll press the start button. And something have failed. I don't know why I did that first time. I just pressed the button again and it worked. Okay, so it finished uploading, but we don't see anything on the counter. And I think I know why. I missed something. Let's hold down the reset. And you can see now it starts counting once every second. So at least our code seems to work, except for one little detail. And of course on these push buttons, the line is always high, and when you press it, you put it low. So it's basically inverted in our code, because we said that the reset is active high. So as long as I don't push the button, then it's in reset mode. So we need to go back and fix that. And thankfully that is not very difficult to do. All we need to do is invert the reset signal before it goes into the counter. And actually we can do it right here. We can write NOT SRST goes to SRST. So this button press is inverted and then goes to the counter. It's not a very good way to do it when you have more counters. Now we will only have a prescaler and 3 counters, but you might get into a situation where you need, say, 100 counters. or 100 different elements that need this reset. And you will have to do this on all of them. And if you forget one, then you're into trouble, because the compiler will not tell you that, and it's not an error. Your hardware will just not work as you wanted it to, and it can be very hard to track down in certain situations. So we don't really want to do this. There's also another fix, of course. Here in the counter, we can just invert the signal here, so we check if the reset is low instead of high. But we don't want to do that, because it could be you're using a module that someone else made, or you don't want to change the code or something like that. So the third option is to make a new local signal. And we'll just copy a line here. We'll call it not SRST to counter. And for good measure, we'll make that a 1 by default. It shouldn't make any difference, because down here we hardwire it to connect to the reset. So we take this, we put the name here, we connect it to not SRST, and we take this name and we substitute here. So now when we press our reset button, it's inverted and it's fed to this signal, and this signal then goes into our counters. So this should work. And if we at some point in time go from having an active low reset back to an active high, then we can just delete this. And of course we might then change the name, because it will not be true anymore. That way you don't have to change all your 100 components down here when you decide to go for another signal. Anyway, back to the NOT, and we will upload it to the board. So it's uploading, and it's coming. So let's try our reset, and it works. And let's also see if we actually get 60 seconds. And we don't. It looks like we only get 59 seconds. But each second we're tracking, it looks like, so it's just we got off by 1 somewhere, and we need to find that problem. And it shouldn't be that hard to find. Actually, I think I know what it is already. You can see here that I think I said that when this becomes true, the output had been 60 for 1 second if we didn't have the -1 here. And that's not true, because we don't take enable into account, so we have to copy this line and put it up here and end it with this one. Before it would only wait for 1 clock period, because this runs at 50 megahertz, and that's not very long time, 1 period. By adding the enable here, we should get the correct value. So let's try that out. We will upload a new file, and it's back to the camera. So I know I promised we would redo this counter and make it into a more simple format, but I don't think it turned out that bad actually, and we are really running out of time in this video. What I was thinking was to make it into a state machine-like structure. That's the way I learned to do it, but it's actually not any easier to read than this. The state machine structure is good for more complex things. That makes it much easier to read what is going on, and we will get back to that, I think, in the future. It has no advantages over this, except that sometimes it's easier to read. So I hope it's okay that I skip it for now. And we are uploading the design, and it still counts. And at some point in the near future we'll also take a look at the simulation tools, where things like this is much easier to see because you can look at the individual clock cycles. If we test it like this, we have no way of telling if the 50 million counts per second is correct, or we're only getting 49.99999 million. It's easy to see if we're off by 1 second, but not by 1 clock cycle. And now it's 1 second. It's just me being a little bit slow to press the button. So this will be it for this video. We got the counter module to work, and we figured out how to make multiple instances of the same file, so we only use one file for all the counters. We looked at port mapping and generic mapping, and I think in the next video we will make a BCD to a 7-segment decoder, so we can put this in a decimal form on these displays up here. So we can just use these small displays until we get the code working, and then we can make a PCB or whatever with the large displays and use some transistors and stuff to drive that. If we have time, we might also look into the simulation, because we will need that later on. And it shouldn't really take that long to make the decoder. So I hope you liked this video, and if you did, please, as always, give it the thumbs up on YouTube. I don't know how long this video was, but probably too long already. If you would like me to divide it into shorter videos, I could also do that, but that way we wouldn't have time to complete a whole module in each video. You're of course always welcome to pause the video and watch the rest of it another day if you don't have time. I know these are getting very long, and yeah. But let me know if you think we should shorten them down, and then we'll take it from there. See ya.